Hello and welcome to Lecture 7 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to calculate the average energy of an ideal gas, and this result will connect our definition of temperature in terms of the derivative of the entropy with the more familiar notion of temperature as connected with the average energy of a gas. Okay, so let's begin by defining the nature of the problem we want to tackle in this lecture. So we're going to suppose that there is a cubic box of dimension L and that we have a particle trapped inside this box. So this is a system, a particle in a box. And this system, which would be our system A, particle in a box, is in thermal contact with a reservoir at temperature T. So it is in a room, in an environment in which the temperature is T. And we're going to suppose that we can measure the state of the particle inside the box. So since the particle is interacting with the external environment, every time we measure its state, we may find it in a different state. So it could be that we find it in one state now, then we take the measurement again in a few seconds or minutes and find it to be in another state and then another state and so on. And we cannot predict the evolution of the state of the particle just because the system is too complicated. So since the state keeps changing, the energy keeps changing. So it does not make sense to ask what is the energy of this particle, since the particle is interacting with the external environment and its energy is changing all the time. But we can ask what is the average energy of the particle. In other words, we can suppose that we take m measurements, then we write down the state of the particle, and of course we write down the energy of the corresponding state as well. Then we can make a list of all the energies that we have measured and calculate the average energy by adding up all the energies we found and dividing this number by the number of measurements that we have taken. So mathematically, we can express the average energy like this. So this is the symbol for the average energy. M here is the number of measurements, and in the numerator, we are adding up all energies we found, all energies we measured. But we are grouping the energies of the state Cn together. So let's suppose that we found the state Cn 20 times. Instead of adding its energy 20 times, we just take the energy of the state and multiply it by the number of times we've measured the state Cn. So this term here is the number of times the state Cn appeared. We multiply it by the energy and we sum over all states. So the numerator is really just the sum of all energies that we have measured. So this is a simple average. There is nothing mysterious in this expression. Okay, so we've just said that this term is the number of times the state Cn appeared in our measurement. Now, as the number of measurements we take goes to infinity, then the ratio of the number of times the state Cn appeared to the number of measurements we took converges to the probability of finding the state Cn. So this is basically the definition of a probability. So with this condition, we can express the average energy in terms of the probability of finding the state Cn. So this ratio here, as m goes to infinity, converges to this probability. So this expression is just a more elegant way of expressing a very simple average. We just add up all the energies we have measured and divide by the number of measurements we took. Now in lecture 6, we learned that the probability of finding system A in a state Cn when this system is in thermal contact with a reservoir at temperature T is given by this expression. This is exactly the situation we have. Our system A now is the system particle in a box, so we can use this expression to obtain the probability of finding our system A in a state Cn. Recall that this term here is the partition function, so this sum runs over all states of system A, our system particle in a box, and this is the energy of the state Cn. So using the expression for this probability that we derived in lecture 6 to obtain the average energy, we replace this term with this term, then the sum will be reduced to this form. So all we need to do now is to evaluate this sum to obtain the average energy. But the job of statistical physics kind of ends here. Now, to evaluate the sum, we need to know what are the states of the system and what are their corresponding energies. But this is not a question of statistical physics. This is a question that quantum mechanics can answer. But fortunately, we have already answered this question in lecture 2. So in lecture 2, we learned that the momentum of a particle in a one-dimensional box is discretized. We use the self-consistency requirement to find the discrete values of the momentum, and we found that the kinetic energy then is given by this expression. We have a very similar situation now. We still have a system particle in a box, but now our box is a three-dimensional box instead of a one-dimensional box. So all we need to do now is to adapt these results to a three-dimensional box. So the wave number now becomes a wave vector, and we need to apply the self-consistency requirement to the three components of the wave vector independently. So Cx here is a natural number, Cy is a natural number, and Cz is a natural number. So these three expressions come from the application of the self-consistency requirement to each one of the components. And now the momentum is of course also a vector. This is the Breuil's equation, and it follows that if the components of the wave vector are discrete, then the components of the momentum must also be discrete according to these expressions that come directly from the Breuil's formula. And we still have that the energy is given by the magnitude square of the momentum divided by 2 times the particle's mass. So using this expression and these expressions for the components of the momentum, we end up with this expression for the energy of the particle in a three-dimensional box of length L. Okay, so now we need to index the states. So recall that when we had a one-dimensional box, each different natural number indexes a different state. Now we have that each combination of natural numbers indexes a different state. So for example, the combination 1, 1, 1 is indexing one state. So this represents one state. The combination 1, 1, 2 indexes another state. 1, 2, 1, another state, and so on and so on. So we could label this state here as n equal 1. We could call this state the state n equal 1, this state the state n equal 2, this state the state n equal 3, and so on. So this sum over n here will be reduced to a sum over all possible combinations of natural numbers. Recall that this sum must run over all states, so we have that the sum must be carried over all possible combinations of Cx, Cy, and Cz to include all possible states. And this term, the energy of state Cn, then will become this term, which is the energy of the state indexed by the combination Cx, Cy, and Cz, and we have just seen that this energy is given by this expression. Okay, so we now use our indexing system to express this sum over here. We've just seen that this sum will be actually represent a triple sum, so this sum becomes a triple sum. The energy here is given by this expression. In the exponential, we have the energy again, so here is the energy again, divided by kb times t. And here we have the partition function. The partition function also involves a sum which must run over all states of the system. So again, it becomes a triple sum. And here we have the energy, which is this term here, divided by kb times t. Okay, so now we just have a math problem. We only need to work out these sums. We're going to work out this sum explicitly later on in the course. We're going to see that we can approximate it to an integral and then use a table. So there's nothing very particularly insightful about working out these sums, so I will just give you the result. So if we evaluate the sum, this is the result we get. This is the result of this sum over here. So according to our result, the average energy of the system, one particle in a box, is proportional to the temperature. Now we can connect this result with the energy of an ideal gas. So in an ideal gas, the particles do not interact with each other. So let's suppose we have an ideal gas of identical particles, and we want to know the average energy of this gas. So there are two ways we could obtain the average energy. One way, we could select one particle of the gas and measure its energy many times over time. Since this particle is not interacting with the other particles, we are essentially measuring the average energy of the system one particle in a box, so we get the same result we've just got. Now, the other way we could take the same average is to measure the energies of all particles in a single instant of time. If we do that, we obtain the same result if the particles are identical. So this is similar to tossing n coins, n identical coins, and counting how many of them lands tail up. We can toss like 1 million coins and count how many landed with tails up, or we could toss a single coin 1 million times and check how many times the coin landed with tails up. The result must be the same if the coins are identical. So we've just seen then that we could obtain the average energy of the ideal gas by measuring the energies of all particles and taking the average. So this average will be the sum of the energies of all particles divided by the number of particles. So that means that the total energy is the average energy times the number of particles. And since we are assuming that the particles are identical, in other words, if we have an ideal gas of identical particles, this average energy is the same average energy of the system a single particle in a box. So it follows that the total energy is given by this term times the number of particles. So with this result, we connect the energy of an ideal gas with the temperature. We found that the energy of an ideal gas is proportional to the temperature. And recall that the temperature here appeared from our definition of temperature in terms of the derivative of the entropy. And we saw that in the previous lecture. So this result connects our definition of temperature with the more familiar notion of temperature as being proportional to the energy of an ideal gas. Okay, so with that we conclude this first part of our introduction to statistical physics, and in the next lecture we're gonna apply the ideas and notions we have been developing to understand the very important concept of chemical potential. So I see you next time.